Okay, this is a new question, and what we've got is it says that there's a force that is required, a 40 Newton force, so let's write that down. An applied force of 40 newtons is required to pull a 10 kilogram wooden block across with a constant velocity across a glass surface on the Earth. So let's just draw a picture of this. There's a wooden block, and here is the applied force. And since it's going with a constant velocity, what that means is, therefore, the acceleration is 0. And if the acceleration is 0, that also means, therefore, the net force is 0. That means that the applied force, this direction, must be counterbalanced by a friction force in this direction, which is equal and opposite. Okay? So if you go sum of the forces is equal to F net, which is 0, that means you've got positive F applied minus force of friction equaling 0. Therefore, obviously, they must be equal and opposite to cancel each other out and produce constant velocity. It says, what force would be required to pull the same wooden block across the same glass surface on the planet of Jupiter? Now, conveniently here, I have the radius and the mass of Jupiter. And so the way to approach this problem is to recognize that the one thing that's going to be the same, if this is Earth, okay, and this is the same block on the same glass surface, but now this is Jupiter, what's going to be the same here and here? Well, the thing that's going to be the same is mu, the coefficient of friction, because it's the same two surfaces. That's not dependent upon gravity. It's actually dependent upon the surfaces themselves. But gravity is going to be different. What's the equation for force of friction? You see, because in this case, the applied force that's required is equal and opposite to the force of friction. But what's force of friction? Force of friction is mu Fn, the normal force. And of course, on a flat horizontal surface, Fn is simply mg. Well, we know the mass, that's 10. That's given to us here. We haven't figured out what mu is yet, but we definitely do know what g is on the Earth. That's just 9.8. Let's go ahead and calculate from this equation where we say, in this case, right, we've got our applied force equaling, well, our friction force. And so both of those guys, applied force and friction force, are both equal to 40 right here. So we say that's 40 newtons. Now that's going to equal mu mg. Let's solve for mu. Okay, so mu is going to equal 40 divided by mg, which is 10 times 9.8 newtons per kilogram. Okay, so what do we get for mu? Well, let's work it out on our calculator. 40, enter, 10 divided by 9.8 divided by, and we're getting mu of 0.41. Okay, approximately. Now, therefore, we know that mu on Jupiter is also going to equal the same amount. But now, the free body diagram looks exactly the same there as on Earth. And so all we need to figure out is What's the force of friction? Because the applied force has to be equal and opposite to it. Well, the force of friction is equal to mu mg. Mu we now know from Earth, which doesn't change. The mass doesn't change on Jupiter. The mass of the block, that is. That's still 10. But g does change. What's g of Jupiter? Well, in order to figure that out, we need this equation. G is equal to gm all over r squared. Fortunately, we've written the values of the mass and the radius of Jupiter previously. We knew we would need that. Mass of Jupiter is up here, 1.90, 10 to the 27. 1.90, 10 to the 27. And divided by the radius, which is 71.5, 10 to the 6. 71.5, 10 to the 6 meters. And remember, that's squared. And what do we get for the g? Here we go. 6.67 EE negative 11. Enter 1.9 EE 27 times 71.5 EE 6 squared divided by. I'm getting a gravitational field strength of 24.8 newtons per kilogram. How does that compare to 9.8? Well, significantly larger. You definitely have to be a lot stronger to live on Jupiter, if you could live there. So now what we do is we take this value of g on Jupiter, Jupiter, and we'd like to put it into here to finish the problem. Okay, because once again the friction force is going to equal the applied force, and that's going to equal 0.41. I'm just basically copying this equation here. 0.41 times 10 times now a known value that we calculated, 24.8. And we're going to get 10 times 0.41 times, and we get a value of 101.6, or approximately 102. Approximately 102 newtons of force. So on Earth, we needed 40, but on Jupiter, because there's more gravity and therefore more friction and therefore more applied force required, we need 100. So more than double. All right? Hope you enjoyed this problem. That's the end.